Can you hear me?
Yes, sir.
Okay. Okay, let's start. Okay, so last time we were pretty much done with the topic of prime numbers. So now we want to move on to how to combine what we studied earlier, that is congruences with prime numbers. And there are some important theorems that we should be aware about. So Fermat's theorem and Wilson's theorem, and a few other things. And
Sir,
actually, yes.
sir, can you give some hint for that? Prove that 1 by p is divergent sigma.
You know what? Actually, I thought we had enough theory to do that, but now I'm not so sure. So I mean, just quickly while I was explaining in the class, this is what went through my head, but I realized there might be issue with that. So if you remember earlier, I had also mentioned the property which we didn't prove, but I stated that for any range of the type n comma 2n, there exists a prime inside that. So I thought, can we use that to prove the divergence? Because if there exists a prime in this range always, then you can do something like basically term by term, you can do something, right? So the first prime P1 is P1 is guaranteed to be less than 2 raised to 1. Second prime is guaranteed to be less than 2 raised to 2, etc. But will that work? I think that
No, sir,
should work.
because if we are considering the RHS, then this time RHS is convergent, and you are considering it that
Yeah,
it will be
exactly.
less than.
Yeah, exactly. That is the flaw which I realized. So I thought this was sufficient to prove that. Because yeah, I mean this will mean is that 1 by P1 plus 1 by P2 plus that whole series is greater than 1 by 2 raised to 1 plus 1 by 2 raised to 2. And RSS is actually can be at most 2. So yeah, that is not sufficient. So I think we need something stronger than this. Um, so
Sir,
maybe
isn't
I was mistaken
yes,
that
sir.
this is very simple proof. Maybe it is not that simple. I think we have to check the literature to know exactly whether this is doable or requires some advanced theory. Let me
For
check
this,
that.
you would require the RHS to be something divergent, so that if you can say that the
Right.
divergent greater than divergent, so it.
Yeah. So basically, we need something. I mean, 2 raised to 1, 2 raised to 2 is a very weak bond. Basically, we need something even stronger than that. That might solve the problem. Let me check. Yeah, I mean, there are, if you just Google it, right, you'll get a few proofs of that. But yeah, I mean, very hard for me to give a hint like that because I've not seen this before. Yeah, in fact, I forgot today what I was going to do was actually plot those three graphs. So the sigma 1 by n, sigma 1 by p, and the sigma 2 raised to y. So just to show that how all of them, I mean, out of that, the sigma 1 over 2 raised to I is convergent, but the other two are divergent. So how are they related relation to each other? I was going to plot that. Maybe if I have some time when we're solving problems, I will do that. Okay. Okay, so continuing with prime numbers, basically now what we're going to try to do is combine prime numbers with congruences and for some important properties. And in particular, what we're going to exploit is the discussion we had earlier about ZP, the set of remainders modulo P, because I think what you'll find today is that we are going to sort of, you can say, kill two birds or even three birds with one stone. So how we can leverage the understanding of the structure of prime numbers or to do multiple things at the same time. So just to recap, what is the notation of ZP? So ZP, assuming that P is a prime, then ZP is the set 0, 1, 2 up to P minus 1. Okay. And here, although we are denoting this as number 0 to P minus 1, recall that when I am writing the symbol I, really what I am referring to is the entire set of numbers which are congruent to I mod P. So this is just a shorthand for the entire set as such, and we know how to do arithmetic on those numbers. So equivalently, you can do the arithmetic on the remainders themselves, modulo P. So it's the same thing. So, and we talked about two operations, addition and multiplication. And so particularly ZP with addition, we said is a commutative group. By the way, the word is typically abelian, is the word used if you refer into textbooks. But what it means is commutative. So commutative means that A plus B equal to B plus A. I mean, the thing is, this property is not required to call it a group, but if you add it, it becomes a commutative group. But group means the other three things. So associativity, the existence of a zero, and existence of inverse. Okay, so if these things are there, it is called a group. Yeah, we saw that under addition, in fact, P doesn't even have to be a prime number for this, so it is always going to be a commutative group. And the other case we saw, if we leave out the zero element, so everything other than zero under multiplication is also a commutative group. Okay. So this was the structure that we saw last time. So we can make a few more comments about this. Particularly if you look at the first set, okay, ZP, the entire set of prime residues, so 0 to P minus 1 under addition. Okay, so so there is a concept called a cyclic group. Okay, so a cyclic group, group G is called cyclic if there exists some element of the set such that, so basically the idea is that can you use some element of the set, the group G, to generate all the other elements, okay, so that for any other element in the group, X is basically G raised to K. So when I say raised to K, it's like whatever is the operation, like if I denote the operation by star, then G raised to K is nothing but G multiplied by G star times. So whatever is that operation. So it could be addition, it could be multiplication, doesn't matter. Okay. For some integer K, or could be a zero also. Okay. So this is what we call a cyclic group. So you can use some one element to generate the entire group. Okay. So how is this relevant for our discussion? So can you try to see, is ZP under additional group or cyclic group? So the first question is ZP under addition a cyclic group?
Yes, sir.
Okay. And by the way, when such a element G exists, it is called a generator. So this G is called a generator of that group. Okay. So yeah, what can be a possible generator for this cyclic group? So the element 1 is itself a generator, right? Because basically 1, 1 plus 1, 1 plus 1 plus 1, etc. So 1 added any number of times will give you all the elements of your group, right? 0, 1, 2, P minus 1. And in fact, after you add 1 P minus 1 times, so you will get the last element. And after that, once more, if you do that, so if you add 1 plus 1 P times, that is nothing but 0. We have cycled over. So you see how the word cyclic is very apt here, because you are going to keep cycling round and round from through all the elements of the group. So if you can denote it pictorially also, that if you start from the, let's say you're talking about P equal to 5, so then the 5 elements can be placed like a clock. So from 1, if you keep adding 1, you'll keep going to the next element, and from 4 will return back to 0. So that is how this is a cyclic group. Okay, so 1 is a generator of the cyclic group. Are there any other generators? What about 2? Is 2 a generator of Z5?
No, sir. Yes, sir. Yes, it works. So I think all the ones which are co-prime to the P would work.
Yes, correct. So if you try to check if 2, so 2 is clearly 2, 2 plus 2 is 4, 2 plus 2 plus 2 is 6, which is 1, 2 plus 2 plus 2 plus 2 is 8, which is 3, and then 5 is 0. So basically when you started with 1, you got this cyclic group. Okay, if I denote it pictorial like this is how 1 went, and this is how 2 will go. So from 2 you will go to 4 to 1 to 3. So it's like just describing a different way of ordering all the elements, but you are guaranteed to get all them. Okay, so what Arnav said is right. Actually, you can generalize this very quickly. So let, in fact, we don't have to consider prime numbers also for now. So let m and n be any natural numbers such that the GCD is 1, and let's say m less than n. Then the claim is that m is a generator of Zm. In other words, if I write m, 2m, 3m, up to the last element, which is n times m. So this whole set, if it we can show that this is a complete set of residues modulo n, then that's what exactly you are saying, that all of these elements will, so this set will be equivalent to the set 0, 1, 2 up to n minus 1 in some order. The order may be different, but all the elements will be covered 1:1 in both sets. Okay. So do you see that intuitively? Because just the way it happened with 2 and 5 here, you can take any two numbers which are co-prime and check that this is going to happen. So I don't know, have you proved this already? I don't remember, but if not, maybe just take a few minutes to think how you can prove this.
Sir, in the definition that we wrote just now of the cyclic group, the star is a function, right? Or
Yeah, it's a function as well as an operator, right? So I mean, it takes two elements as an input and generates an output. So if you write it as a function, it will look like goes from G cross G to G. So,
okay,
but
sir.
just for a shorthand, instead of writing star of A comma P, it is more customary to write A star B, but it means the same thing.
Okay, sir. Yes, sir.
And actually, in group theory, if you see the entire literature even doesn't use the, see here I use star to highlight that it could be any operation altogether, but in group theory properly, it's often denoted by multiplication only. But just because it is denoted by multiplication should not fool you into thinking that it is about multiplication, so to say. It can be any operation. So it can be addition also. But it's just more convenient because you can quickly write g raised to k and things like that. Right? So we are used to the multiplication notation. Okay, so how do you prove this?
Sir,
That
what is the third last word you've written?
a complete set of residues modulo residues or remainders, any word is fine. Okay, so how do we prove this? Effectively, what I have to show is that these two sets are identical. So the first set, if I call this L and R, so I want to show that these two sets are identical modulo N.
Sir,
So
can I try?
yes, go ahead.
Sir, if we assume that some of this, so there exist two elements of the L that are congruent modulo n,
Hmm.
then we can say that so and let those be some k times m
Yeah.
and
Okay.
something like that. Sir, actually not k times n because we are taking the m only.
Oh, sorry. X and Y.
Yes, ma'am. Xm comma ym.
Okay,
So
sorry.
xm is congruent to ym mod n.
Yes.
And also we note that x comma y belong to 1 comma 2 comma dot n.
Yes.
So if we take the difference, then we get that n divides m times x minus y.
Correct.
Since n and m are co-prime, we get that n divides x minus y, and by seeing the range of x and y, we get that x is equal to y.
Yes. Correct. Okay. Does everybody follow? The two important ideas here. One is that because n and m are co-prime, that is important because then we can apply Euclid's lemma and cancel it. Otherwise, you won't be able to do that. And once you cancel it and you get n divides x minus y, and the fact that x and y belong to the range 1 to n, so any two multiples of n cannot be closer to each other than n minus. Yeah. So with both of these, what we have shown is that any two elements in n have to be incongruent modulo n. Okay. So that is one thing, and the second thing is obvious that the number of elements in the LHS is equal to that in the RHS. So in some order, they are forced to be equal to 0, 1, 2, up to n minus 1. Okay, and it's a good idea to visualize this for a few numbers just to appreciate how this is happening. So I mean, if you take a slightly larger number, like let's say you take n equal to 9 and m equal to 2, let's say. So then you'll see how it basically describes a star of that order. And in fact, there is some notation. Just as you have regular polygons, you have a concept of regular K stars. Okay, so these are 9 element points. So if you start with 0, 2, 4, 6, 8, so that is the order in which the residues will be described. Then 1, 3, 5, 7, and 9, which is back to 0. Okay. So like that, for every co-prime pair, you'll get a star, which starts at 0 and completes at 0. And here you can appreciate why the co-primality is important, because if you started with a number which was not co-prime, let's say you took m equal to 3 instead, then you'll from 0 you'll go to 3, you'll go to 6, and you'll return back to 0 without reaching all the elements. Okay? So for that reason, the co-primality is important. Okay, so having understood this, what can be the implications of this? So this set L, which is M2, M3, M up to NM, and this RHS. M2, M3. So what if we multiply all the elements of LHS? So let's say M into 2M into 3M into up to NM. Okay. So I'm multiplying all the elements of that first set. We can agree that even the order may be different, but the product will turn out to be identical, modulo n. So this has to be congruent to what is that? 0, 1, 2, n minus. And out of that, let's leave out the last term, because the nm is going to be obviously divisible by n. So it will make the whole multiplication 0 modulo n. So let's leave out the last term. Okay. So let's terminate the calculation at the second last term, n minus 1. So this is going to be congruent to 1 into 2 into 3 up to n minus 1. Okay. Modulo n. Okay. So appreciate that the elements are not term by term congruent. So m may not be congruent to 1, but m is going to be occurring somewhere in the RHS. Okay. So through some reordering, all the terms on the LHS and RHS are going to be equal. That is why the product is equal. Okay. So then if we simplify this, what do we get? So we get m raised to n minus 1 into 1 into 2 into 3. So in other words, this is just n minus 1 factorial, right? And on the RHS also you get n minus 1 factorial. So what you're getting is n minus 1 factorial times m raised to n minus 1 is congruent to n minus 1 factorial modulo n. Okay. So this is a very interesting property, and looks like n minus 1 factorial is there on both sides. So it's very tempting to cancel it, right? But in general, you realize that we cannot cancel it because if you remember what we had done when we started congruences, I mean, if you have some AK congruent to BK modulo M, then what is the condition under which K can be cancelled?
GCD of K and N is 1.
Okay, so if K and N is 1, then we can cancel and say that A congruent to B mod M. So this is where we are going to kill two birds with one stone. First approach is, see, I want to cancel this. I can either change this, I can choose N in such a way that GCD of this and this is going to be 1. Or why don't I have to take all the products here? So we can do something bit more clever over there. So we'll come to that later. But first step, what is the value of N, where N minus 1 factorial and N will have a GCD of 1? So if a GCD of N and N minus 1 factorial has to be equal to 1, what can be the condition under which that will happen?
N is
Has
prime.
to be relatively prime with all the numbers before it. So it
Yes.
has to be a prime.
Correct. Right. Prime numbers are the only numbers which are co-prime with all the numbers occurring before that. So therefore N is a prime. Okay, so if we assume that N is equal to is a prime number and let's start replacing N with P. So then what we are saying is that P minus 1 factorial into M raised to P minus 1 is common to P minus 1 factorial modulo P. And now we can cancel this from both sides. And what we are left is what is called Fermat's little theorem. And of course, where it is only applicable where M and P are co-prime. Okay. Because if M is not co-prime to P, then LHS is obviously 0. Okay. So this is called Fermat's little theorem. And I mean, in most contexts, you can just call it Fermat's theorem. That is also okay because the other Fermat's theorem is way more complex than this. So this can be useful to do a lot of calculations very quickly, and we'll see examples of that soon. Okay. But just to cycle back to what I was saying earlier about how we can try to do this in a different way. So here, one way we found was we restrict the value of N. So we made N a prime number so that we can cancel N minus 1 factorial safely from both sides. But now I'm saying let us revisit the calculation and see if we can do something else. See this, why does this N minus 1 factorial occur? Because we are taking 1 into 2 into 3 into N minus 1. Where these elements we had got from the original sets L and R. Right? But now I'm considering a slightly different definition of L and R. Okay, so our original L was simply all the numbers M, 2M. In general, if I just write L was just K times M for all K in the range 1 to N minus 1. Okay. So I'm going out to N minus 1 only. As I said, we'll leave out the last term NM because that is obviously 0. And the RHS was 1 to N minus 1. So the problem occurred because we wanted to cancel that factorial product, but that was not co-prime with N. So why don't we consider a new definition of the set L? So now let me consider the set of all numbers such that K is still in this range. But in addition, I also put the condition that K and N are co-prime. Okay. So I'm only considering the co-prime factors of N in this product and same on the RHS. So RHS is all the numbers in the range 1 to N minus 1, but which are co-prime to N. Okay. So I would consider all the numbers between 1 to N minus 1, only the ones which are co-prime. So if you want to take a concrete example, if let's say we are talking about N is equal to 10, okay, then the R will look like it will be only the numbers 1, 3, 4, not 5, 6, 7, 8, 9. Okay. So these will be the only elements in RHS if N is equal to 10. And let M will equal to 3, let's say. So then LHS will be 3 into 1, 3 into 3, 3 into 7, and 3 into 9. Okay. Something like that. So now what will happen? We'll do the same thing as before. So just to give it some concrete names, instead of writing this set as L, I can write L as some K1 times M, K2 times M. So we don't know what the K1, K2 are in general. Okay? And let's say the last term is KR times M. Okay. And in RHS will be simply the K1, K2, KM. KR. Okay. So once more, I would like us to check, can it be that L and R are, so now there will not be the complete set of residues because clearly we have dropped some terms. So we will not get all the remainders, but my claim is that L and R are identical under reordering, okay, modulo N. So the claim is that L and R are identical modulo N under rearrangement or in some order. Okay. And maybe you can check that in this numerical example. So here the RHS was 1379 and LHS is this number. Let me simplify that. That is 3 into 3 is 9, 3 7s are 21, which will be equal to 1, and 3 9s are 27, which is equal to 7. So you see how this RHS was 1379 and LHS is 3917. So it is the same numbers, but just in a different order. So this will always happen.
Sir, in the definition of OR also shouldn't you consider closed interval?
It is, I think my handwriting was, it is, both of them are closed.
Okay, sir.
Or let me just write it in, instead of writing it this way.
Sir, because if you write interval, then you'll also specify that K belongs to Z.
Yes, yes. Yeah. I mean, I think that is implied here, so we do not rewrite that every time. Maybe just let me write it this way. Okay. So, yeah, maybe take some time to think how we can prove this result.
Sir, I think I got some idea.
Okay, maybe just
Yes,
wait
sir.
for a couple of minutes. Okay, so anybody other than Arnav who has made some progress? Okay, I'll give you a hint. See, what we want to show is that there is a one-to-one correspondence between the two sets, right? So you can break this problem in this way, that for prove that for any element in the LHS, so for any a or any I in the range 1 to R, okay. Okay, so if you consider the ith element in the LHS, which is Ki times N, will be congruent to some Kj. So there exists some J in the same range 1 to R, such that Ki times M is congruent to Kj mod. Okay. So if I denote it pictorially, if I show the LHS and RHS as two sets like this side by side, so K1M, K2M, KRM, and K1, K2, KR. Basically, we want to establish some kind of bijection that every element on the LHS will be equal to some element on the RHS, and so in that way, there will be a one-to-one correspondence between the two sets. That is what we want to show. Yes, Adya.
Sir, I'm not sure, but since M and N are co-prime, so M which we will be choosing, it should belong to R.
No, sorry. Can you repeat the last part?
Sir, since M and N are co-prime,
Yes.
so the M which we are choosing, it should belong to R.
M which we are choosing should belong to R. Yes, that is true. No, when you say belong to R, what does that mean?
Sir, because R is the set which in which all the terms are co-prime to N.
Yes, yes. Okay, got it. Yes, correct. Okay. So then,
Then if N is one among K1, K2 till KR,
yes.
then you know that K1 is congruent to something modulo N, and similarly, and the another term which we are taking, if it is Ki, then Ki is also congruent to something modulo N. Then Q1 into Ki will be congruent to the multiplication of those two.
But why will it belong to the R? That is the question, right? See, R doesn't have all the remainders now. So, can it be that some LHS term like Ki into M is not so? Like for this one-to-one mapping, what if there is some element which is left out? That some element does not have a corresponding matching term on the RHS. That is what we want to eliminate. That cannot happen. See, intuitively we know this should not happen, but we need to prove it somehow. Okay. So do you see that if we prove this part, that I think basically what Ajay you are saying, I'm trying to formalize the same thing, that every term like Ki into M on the LHS is congruent to some term Kg on the RHS. That is what we want to show, that some such Kg will exist. Okay, Arnav, is your proof along the same line or something different?
No, sir, something different.
Okay. Then maybe I'll just try to complete my approach and then
Yes,
come
sir.
to yours. So this is what I have to do, that such a J exists. So this is how we can approach it. So clearly, whatever is Ki M, okay, I can obviously divide it by N and get a quotient and a remainder. Okay, let me not use small r for the remainder. Yes, okay. So there exists some Q and S such that if I divide Ki M by N, I'll get this, and S is in the range of the remainders. Okay. And clearly, what will happen? Can S be 0? S cannot be 0 because I mean KIM, both Ki and M are co-prime to N, right? So their product cannot be a multiple of N. Okay. So S is not 0, which means that S is in the range 1 to N minus 1. Okay, so therefore S is in the range 1 to up to N minus 1. Okay. And in addition, can we also claim that S is going to be co-prime to N? So GCD of S and N, do you see why that has to be also equal to 1? from this expression, because in this expression, this term is co-prime to n and q1 is a multiple of n. So therefore kim is congruent to s. Okay, as k1 ki times m is co-prime. Okay, so if this whatever is this remainder is co-prime, clearly it has to belong to the RHS, right? So therefore this s has to be an element of that k1, k2, kr's. Okay, so there will exist some index j such that s equal to kj. Okay, so there will exist some j such that s is equal to kj. So what we have proved just now is that for every element on the LHS, there will be some matching term on the RHS. Okay, so for every term, there will be some corresponding term. So are we done, or we need to show something else also here? We only showed that every element on the LHS has a matching term on the RHS, but to show identical nature, you have to show the one-to-one correspondence, right? What if the picture is something like this? Let's say you have 3 points on the LHS, 3 points on the RHS, and the picture is something like this. So this will not work. We need every term on the LHS to have a unique term on the RHS. So there are 2 ways to show it. Either prove that, so this was the first part, you can say that, so this is like part 1.
Sir, I think we have already shown that in the last problem.
What did we show?
Since this L, what we will consider now as a subset, is a subset of the last L which we
Right.
considered. And
Yeah.
in the last problem, we showed that none of the 2 are congruent mod n. So
Yes.
the arrows won't be crossing.
Yeah, that's a fair point actually. So yeah, we already have done that, so that we already know that all the elements of the LHS are incongruent modulo n. So therefore this will never happen. So therefore all the RHS, the capital R already has equal elements to the LHS. So number of arrows leaving LHS is equal to the number of arrows reaching RHS, and no 2 of them will point to the same element. So therefore the 2 elements will be congruent. There is one more way to look at this. What we did here was we started from an element of the LHS and reached the element of RHS. I want to show the converse, that for every element in the RHS, okay, so for every index j in that range, if you consider the element of RHS, which is kj, then I want to claim that there exists some ki such that ki times m is congruent to kj mod n. Okay, so I'm actually doing the reverse mapping, that if I start with any element on the RHS, there will be some corresponding element on the LHS, some ki times m, which will be congruent. So if we show it this way also, this is like traditionally what we call a bijection, right? From every element of the LHS, you go to the RHS and vice versa. So why will such a ki exist? This goes back to simply the linear congruences theory, right? So here, what we know is that kj is kj's GCD with n is 1. So if we know this, then in this congruence, where if you treat this ki as an unknown, right? So if I consider the equation x times m is congruent to kj modulo n. Okay. So this is going to guarantee to have a solution, because k comma n is 1, kj comma n is 1. So there exists some x in the range 0 to n minus 1, such that this equality will be true, this congruence will be true. And now it simply is a matter of checking that. So we got a term of the type x times m. Will this x times m term belong to the LHS, right? So if we show that x, the GCD of x and n is also 1, then clearly x is going to be ki for some I. So is that going to be true, that GCD of x and n is 1? Again, same as what we did earlier. When we wrote the division algorithm to obtain the remainder, the same thing can be reversed here, because this can be rewritten as xm is equal to kj plus some q times. Okay. So here again, if you see both LHS and RHS, if the GCD of what we already know is that the GCD of this is 1 with small n, and this will not make any difference. So therefore, the GCD of this is also going to be 1. And if the GCD of x into m is 1, then the GCD of x will also be 1. Right? So GCD of x into m n is 1 will imply that GCD of x comma n is also 1, because we can ignore m over here. Okay. So this is how so there are two proofs that we could do for the second part. First is what Arnav said earlier, that we already have shown that two arrows on the LHS cannot intersect on the RHS. And second is that we explicitly show an inverse mapping. So these two things are going to be universal, not just for this problem. Okay, anytime you want to show that there exists a bijection between two sets, right? In general, if we have two sets A and B, and to prove that there exists a bijection, to prove that some function f is a bijection, what we need to prove is first prove that so part one is that for every element in the LHS, the corresponding function, the output lies in the RHS. And the second part can be done in two ways. So the first part is that through that for all elements in the RHS, there exists you can define an inverse function such that the inverse of the RHS will be in the LHS. So this is like two-way mapping. From first you go to the right, and the right you go back to the left. So in addition, I think here, because we had finite sets, so we didn't have to do this. But in addition, you also have to show that any two elements on the LHS, the fact that the two arrows don't intersect. Okay, so that you also have to show that. So for any two elements A1 and A2 which are not equal, their corresponding mapping will also be not equal. Okay, so this is like the more general case that you have to do if you have infinite sets and things. Okay, but anyway, coming back to the problem. So what we have shown is that those two sets, capital N, capital R, now they don't have the entire set of residues. They just have the co-prime residues. But what it allows us to do, when we did earlier, we multiplied all the terms together, right? So when the first set was comprised of K1 times M, K2 times M, Kr times M. And the second element is set is simply K1, K2, Kr. Okay. Same as before for Fermat's theorem, what we did, if you just multiply all the elements of the first set and the second set, on the LHS, what you'll get is K1 times K2 times Kr times M raised to R is congruent to, on the RHS is simply K1, K2, Kr modulo. And now the advantage is that because we have taken only the co-prime terms, so this product and this product can now be safely cancelled from both sides, even if n is not a prime number. Right? So if I cancel it, what I get is M raised to R is common to 1 mod. Okay, so this is Euler's theorem. Okay. So what is R? This R was the number of terms in these two sets, L and R, right? So R is actually the number of integers in the range 1, 2 of n minus 1, or you can take n also, which are co-prime to n. Okay. And there is a notation for this, it is called a pi function. So it is denoted very simply by pi of n. Okay. So pi of n is the number of integers in the range 1 to n which are co-prime to n. So instead of writing R, you can write this as m raised to pi of n is common to 1 mod. Okay, so this is Euler's theorem. And if I just go back to Fermat's theorem, I'll just copy it here. So this was Fermat's theorem. I mean, I just put the two of them side by side and see how similar they are looking. In fact, as it turns out, that Fermat's theorem is a special case of Euler's theorem, because for any prime number, right, what is the phi of p be? The number of terms which are co-prime to p
P minus 1.
is p minus 1, right? Because 1, 2, the entire set is going to be co-prime to p. So therefore, if you substitute that in this expression, you will get Fermat's theorem. So Euler's theorem is actually generalization of Fermat's theorem. But again, the condition is m and n are co-prime. Okay, so in a way, I say all of this was possible because of the starting point that ZP is a cyclic group, ZP under addition. So in a way that the starting point was the ZP, or in fact Zn doesn't have to be even a prime number. Under addition is a cyclic group. That is what led to all of these things. Okay. So now coming to the other set, or rather the other operation. So what about multiplication? So if you consider the set, and now this time you have to consider only prime numbers. So if you consider ZP upon 0, which is the set of all non-zero terms, so 1, 2, 3 up to p minus 1. And now the operation you are considering is multiplication. Okay. So then the question is, and I don't want to write ZP slash 0 every time, so let me just call it ZP dash for short. Okay. So ZP dash is the set of all non-zero residuals modulo p. So now the question is ZP dash cyclic? And the operation is multiplication now. So sometimes it is denoted like this as a two-pair term. So the first is the set itself, and the second is the the operation you are considering. So is this set cyclic or not? So what do you think? If you have done any small experiments?
Sir, I think it is cyclic, but I'm not able to generalize the generator.
Okay. Okay. So I don't honestly know if this proof is within our scope or not, but the short answer is yes, it is true. So in other words, so there exists a element A in the range 1, 2. So it cannot obviously cannot be 1 because 1 raised to 1 raised to 1 will not give anything. So it has to be in the range 2 to p minus p minus 1. In fact, you can see quickly that cannot be p minus 1 also, but and for now let me just write it this way. Such that a square, a cube up to a raised to p minus 1. So this whole set of all the powers of A is identical to the set of the ZP dashes. Okay, and modulo n. Okay. Again, same as before, that the order may not be preserved, but the entire set of elements from 1 to p minus 1 will occur. Okay, and if this happens, then A is called a primitive root of P. So A is called root of P. Okay. So the claim is that every prime number does have a primitive root. I think we'll have to do a lot more reading before we can prove this, that the fact that such a primitive root always exists is not very easy to see actually. Because see what will happen, because of Fermat's theorem, what we know is that any element A you take, A raised to p minus 1 is going to be congruent to 1 modulo P. That is what Fermat's theorem tells us. But what Fermat's theorem doesn't tell us is that what if some element before p minus 1 becomes 1? That is quite possible, right? Maybe you start with a square, a cube, but somewhere in between some a raised to k is congruent to 1. That can always happen. That is not excluded by Fermat's theorem. But one thing you'll notice, suppose this happens, okay? Suppose, and there is a name for this. Okay? So what we define the smallest exponent k such that ak is congruent to 1 modulo p as the order of a modulo p. Okay. And this is for any element A, so it doesn't have to be primitive root. For any element A, the smallest exponent such that a raised to k is congruent to 1 mod p is called the order of A mod. Okay. And so, in particular, if there is a term for which the order is p minus 1, then that is a primitive root, right? So the claim is that, can you see why the order of A has to be a factor of p minus 1?
Yes, sir, because a raised to p minus 1 is always congruent to 1. So,
Yes.
sir, in the above statement, where you have written there exists a belongs to 2 comma dot comma p minus 1, do we have to mention that where p is not an odd prime, where p is odd prime, because if p is 2, then that statement makes no sense.
Yeah, in general, I've been assuming that p is a sufficiently large prime number, but I think, yeah, it's even for odd prime number, if p is 2, see, if p is 2, then trivially the set we are talking about is simply the
Yes.
singleton element, right? So here 1 is its own primitive root. So I think we can safely say we are talking about p greater than 2.
Yes, sir.
Just to take some concrete examples of the order. So let's say we are talking about, I don't know, let's say take p equal to 7. So if I take p equal to 7 and consider all the numbers, so our set ZP dash is the set 1, 2, 3, 4, 5, 6. Okay. And if you start to write the order of each term, so order of 1, the order of 1 is trivially 0 because, I mean, or no, I don't know if we can call it 0. Maybe you have to say the order of 1 is undefined. Because otherwise, if we allow 0 to be the order, then all the order of all the elements will be 0. So maybe let me not define the order of 1. I'm not sure. Okay, but from the other, so order of 2 is the smallest term. So if you consider 2, 2 square, 2 cube, etc. So you see what happens. Modulo 7, 2 cube, which is 8, which is already congruent to 1. So order of 2 is simply 3. So which means that at least this is not a cyclic. This is not a generator. Okay, 2 cannot be the generator of the entire set because, I mean, if I write all the elements, it is just repeating the same element twice. So this once you reach 1, right, then the elements will simply cycle over. So this is 2, 4, 1, and this is again 2, 4, 1. So we have not generated all the elements of your set. Okay. Continuing. Then what about 3? So order of 3. So 3, 3 square, 3 cube. This looks to be all distinct, right? This is 3, modulo 7 if you go. This is 3 mod 7, 3 square is 9, 2 mod 7, 6 mod 7, 18, 4 mod 7. So you see, all powers of 3 are covering all the residues, and there is no repetition. So order of 3 is 6, and it also means that 3 is a primitive root of 7. Okay, but see how examples of 2, right? Powers of 2 are cycling back. So it is not a trivial claim to make that for every prime number such a primitive root will exist. But if you are curious to know more about that, I don't know if Burton also covers this. So chapter 8 in Burton talks about primitive roots, but I don't remember if they talk about the existence of a primitive root, or if not, you can try to find it online. Okay, but regardless of that, whether or not a primitive root exists is another thing. But there is a slightly different consequence of this. So what happens if we multiply all the terms of z p dash? Okay, so consider the product of all the numbers. So 1 into 2 into 3 into up to p minus 1. Okay, so this is the product of all the terms in the z p dash. So out of that, let us leave out the first term and the last term. Okay? So let us leave the first and the last term aside. Okay, because we are going to consider this product modulo p. Okay? So of course the product is p minus 1 factorial, which we know. But what is the remainder modulo p is the question. So out of that, the first term is obviously 1 modulo p, and the last term is obviously minus 1 modulo p. So if you leave those two aside, what happens is that either you can see it either through the fact of the generator being existing, or simply through basic calculation. You can see that we can pair up terms in the range 2 up to p minus 2, such that so we can form pairs such as a comma a dash. Okay, such that a into a dash is common to 1 model. In other words, this is simply the existence of an inverse, right? For every element a, there exists some term a dash such that their product is 1 mod. And here in particular, that number is going to lie in this range 2 to p minus 2. Okay. And important for pairing, to achieve such a pairing, a and a dash have to be distinct. Okay. So where A and A dash are also distinct. Okay, so for that distinctness, we have to leave out the first and the last term because one is its own inverse and P minus 1 is also its own inverse. But every other term will have a distinct different inverse. That is what we are claiming over here. Okay. So in a way, we already proved this earlier. So I mean, what we proved is that the inverse exists, but we didn't prove that the inverse has to be distinct from A itself. But I think that is also easy to see that if it was the case that A is common to A dash modulo P, then what will happen? Basically, we are saying that A square is common to 1 modulo P. And this will imply that P divides A square minus 1. And so therefore P divides A minus 1 or P divides A plus 1. And both of these cases are not possible because we are strictly talking about the remainders from this 2 to P minus 2. Okay. So we have deliberately left out the two corner points. So therefore, none of this is possible. Okay. So therefore, the number of terms from 2 to P minus 2 is clearly an odd number, even number, and they can all be paired one at a time. So what will the entire product be equal to then? This entire product 1 into 2 into 3 into P minus 1 modulo
minus 1.
minus, right? Because the first term was 1, everything else in between will be 1 into 1 into several times 1 into 1 into 1, right? Every pair that matches up will create a 1. And the final term is P minus 1, which is congruent to minus 1. So therefore, what we get is the entire product, which is P minus 1 factorial, is congruent to minus 1 modulo P. Okay. And this is called Wilson's theorem. And as it turns out, the converse of Wilson's theorem is also true that if something like this is satisfied, then P has to be a prime number.
Isn't that obvious because otherwise P would divide the P minus 1 factorial?
Yes, it's correct. Yeah, but I think in particular the thing is Wilson's theorem, the converse is true. Fermat's theorem, the converse is not true. I think that is the key point. Fermat's theorem, as we saw, that there can exist numbers such that A raised to P minus 1 is common to 1 mod P, even if P is not prime. Okay, so just to illustrate Wilson's theorem in a concrete example, let's say if we take P equal to 7, then the numbers of ZP dash are 1, 2, 3, 4, 5, 6. Okay, so how will the pairing go? 1 and 6 you have to leave alone. So 1 is common to 1 and 6 is common to minus 1. Okay, but everything else. So for example, I think we can make the pair 2 into 4, which is 8, and 3 into 5, which is 14. Okay. So therefore 2 into 4 will be common to 1 and 3 into 5 also common to 1. So that is why when you multiply everything together, all the pairs in between get cancelled out and all you're left with is minus. Okay, so I mean we saw 3 important theorems today: Fermat's theorem, Euler's theorem, and Wilson's theorem. So all of them are expressed in terms of some congruences. But I think pretty much these are some of the important theorems you require for some problem solving. I mean, to be honest, I didn't find too many problems which use this, but once in a while it can be useful. And for some simplifying some calculations also, like if I ask you some question like find the last 4 digits of some big number, okay? Let's say that if I give you 2 raised to 999, and if you ask what is the last 4 digits of this, okay, then you can do a lot of simplification using these theorems to quickly arrive at the answer. So, I mean, you can take this as an exercise if you want how to quickly find something like this. But beyond that, I mean, see how we approach the proofs of all of this. We are not just doing the proofs, but we understood the structure of ZP, and that is like a starting point to a lot more number theory that is going to come ahead. Unfortunately, see for Olympiads in a book like Burton, after chapter 8, the topics are not that relevant. So that is why we don't do them. Instead, we turn our attention towards more problem solving. But I strongly encourage you that if you are liking number theory or you want to develop your interest in number theory, do look at those chapters, because that is like where the really interesting number theory starts to happen. Okay, you have the quadratic reciprocity law, you have we have linear congruences, but we not talked about quadratic congruences, right? X square is congruent to 1 mod p. So what happens there? So what is called the Pell's equation? All of those interesting things are covered in the later chapters of number theory in inverter. So I would urge you to look at that particularly. I mean, practically speaking, also, I agree that it is not directly useful for Olympiads, but it will develop your problem solving techniques. You will become so strong in mathematics that Olympiad will start looking trivial to you. Okay? And I'm not just saying this. In fact, if you look at some of the most successful competitors or medalists in the recent history, one thing I'll say in common to all of them is that they don't restrict themselves to Olympiad. They become stronger in mathematics, and then Olympiad is just a consequence of that. So you have to get into that mindset that you really start liking the subject and go deep into that. Even if directly you will find that it's not useful for any exam, but indirectly you'll develop a lot of skills about how to apply different problem solving techniques, how to develop your rigor and things like that. Because see, we are pretty much reaching the tail end of the theory part of number theory. Maybe one more lecture to cover some things which I have not covered, such as I think number theoretic functions. So I just referenced phi of n, but not talked about how to obtain the formula for that Euler's function and things like that. So those things will be done in 1 or 2 lectures. But following that, we are going to dedicate all our time to problem solving practice. But don't let that discourage you from exploring as much theory as you want on your own. Okay, so with that, as I said, there are a few things remaining which I'll cover as theory for the next time, but I want to turn our attention to some problems now. So just give me a minute. Okay, so I hope you can see the screen. So up to question 8, we are already done last time. I've added question 9, 10. In fact, I added 1 or 2 more questions also, but I didn't get updated. Just give me a minute. So you can try questions 9 to 12. I think they are roughly in increasing order of difficulty, but no, 3 question 12 is simple. Anybody has done the first problem, question 9?
Yes, sir.
Okay, so question 9. This is very clearly inspired by Euclid's proof of infinitely many prime theorem. So what are the first few terms of this sequence? So P1 is 2. P2 is the largest prime factor of 2 plus 1, which is 3. P3 is 7, and so on and so forth. So if possible, let some nth term Pn equal to 5. Which means that 5 is the largest prime divisor of the product before that. So if I call that S, P1, P2, Pn minus 1 plus 1. So this S, so 5 divides S. S and 5 is in the form.
So sir, it should be a power of 5
It should be a power of 5. Why is that the case?
because this 5 is the largest prime divisor and 2 does not divide S and 3 does not divide S.
Yes. That's the important observation, that in this list 2 and 3 are already occurring. So K is clearly not a multiple of 2 and 3. And the way that this Pn are defined, if Pn is equal to 5, it means that no prime greater than 5 is a factor of K, right? Therefore, K has to be some 5 raised to T, let's say. So then what is the problem? Can it be possible that P1 into P2 into Pn minus 1 plus 1 raised to T?
No, sir, this won't be possible.
Okay, why?
Because if you, after subtracting 1 on both sides, you get that P1, P2 all the way to Pn P
N minus 1.
and minus 1 is equal to 5 to the power n. 5 to the power n minus 1.
Yes.
So we know that 4 would divide the RHS.
Right. So 4 divides LHS. Okay.
Yeah, so which means 4 has to divide the LHS also.
Yes.
But if you see the only even factor of LHS is going to be 2.
Okay. So P1 is 2, we know that. But the
Yes.
question is, why can there not be another copy of 2 in this?
Because all the other from P2 onwards all are going to be odd.
Yes, all of them will go. So if you're writing this in the exam, it would be good to break this into this kind of lemma. So lemma 1, prove that all Pi for I greater than 1 are odd. Okay. That will be the first step that will help you to establish the fact that we will get a contradiction over here. Okay. So then once you have this lemma, then the proof is complete, right? Because then 4 divides this product implies 2 divides P2 up to Pm minus 1 this product, and which is not possible. If all of them are odd, then product cannot be even. Okay, does everybody follow this chain of reasoning? So it was a simple question. Just observe and choose the right modulus. So this is one important trick that you will learn from this problem, that here importantly we observed RHS is 5 raised to T minus 1, which is congruent to what 1 mod 4. That is what helped us to do this problem. Or not 1, sorry, 0 mod. I mean basically 5 raised to T was congruent to 1 mod 4. That is why this became 0 mod. Okay, so choose the right modulus, and that is all we need to do for such problem. Okay, I think because this is a very simple problem, I don't expect any alternate solution. But if anybody has any ideas, let me know. Okay, then moving on to the next problem, question 10.
Sir, can you give 2 minutes for question 10?
Sorry.
Sir, can you give some time for question 10?
Yeah, sure, take your time. And just a minute, they are updated. Okay, any progress with question 10?
Sir, I have got two solutions for fractional part of x less than 0.5. I am trying for fractional part of x greater than 0.5.
Okay. See, for fractional part of x greater than 0.5, just looking at the LHS and RHS, you will see it's difficult for them to be equal.
Why, sir? I did not get like what was your intuition?
I mean, if you just compare the magnitude of LHS and RHS, right? See, LHS is the reciprocal of two integers.
Oh yes, sir. I think it's quite simple then, because the sum of reciprocals will be less than 2, while the RHS
Yeah.
will be greater than 4.5.
Yeah, exactly. Okay, so just to start from the beginning. So the question given is 1 over fractional part of x. Okay. And I think the question did not clearly state the range where the LHS may be undefined. So we have to take care of that ourselves. So in any question which involves greatest integer term and things like x and 2x, always the right approach is to try to make cases. Basically, we don't know when this 2x will jump. If you look at the graph of as x is increasing, of course, when x is an integer, then 2x will also jump at that point, but it will jump at the fractional half intervals also, right? So to make cases for that, if you just write x is equal to the integer part of x plus the fractional part of x. Instead of writing this every time, maybe just simplify it by writing it as k and r. Okay. So where r is the greatest integer, so r is in the range 0 to 1. So if x is k plus r, then 2x is 2k plus 2r. And now the question is this still a valid splitting, as is this integer part and fractional part? So for that, we need to make cases. Now 2r is clearly less than 2. But the question is it greater than 1 or less than 1? So that is the cases, right? So case 1, you can say is that, let's say 2r is less than 1, which means that the greatest integer of 2x, 2x will be 2k, right? So then you can very quickly rewrite the given expression as 1 over k plus 1 over 2k is equal to 9r plus 1 by 3. Okay. So here again, before you start writing any further simplification, just look at the expression and see what's happening. Right? See, RHS is 9r plus 1 by 3. So clearly, RHS is not very small in the sense that it will be at least greater than or equal to 1 by 3. So that puts some constraint on the LHS. That see, if you keep making k larger and larger, clearly the LHS is going to become smaller and smaller. But it cannot become so small that it will drop below 1 by 3. So that should help us to get some bounds on the value of k. So LHS is, by the way, how much is it? 3 by 2. Right? So what we clearly see is that 3 by 2k has to be greater than or equal to 1 by 3. So therefore, if you rewrite this, k has to be less than or equal to. By the way, before even we do any of this, I think it's important to eliminate the case that x is less than 0. Do you see that x has to be greater than 0? In fact, greater than 1, in fact. So I think we have to start with that. So what will happen if x is negative?
Then LHS is negative, but RHS is positive.
Yes. X plus negative, that way LHS will be negative and RHS is positive. So it cannot happen. So x is clearly greater than 0, but not only that, if x was in the range 0 to 1, then the LHS is undefined, right? So x has to be in fact greater than or equal to 1. So that we can say upfront. So I mean, therefore this k is positive basically. So we can freely exchange it on from LHS to RHS. And so what you get is k is less than or equal to 9 by 2. So which means that k is basically in the range 1 to 4, right? So k is either 1, 2, 3, and 4. Okay, and in each case you can try and see if basically you substitute the value of k, you get some value of r, and as long as that r satisfies the condition 2r less than 1, then that is the valid solution. So I mean, if I just rewrite the given expression, what do I get? Keep r to one side and take everything on the other side. R is 1 by 9 of 3 by 2k minus 1. Okay. So now in this, just substitute, and maybe we can simplify this bit further. 1 by 6k minus 1 by 26, right? So if k is equal to 1, then what is the value of r, etc. Right? So k is equal to 1, 2, 3, 4, you can try. And which of them give valid solutions? Actually, I have
1
not
and
completed.
1 and 3.
1 and 3. So k is equal to 1 and k is equal to 3. So it is 1.
Then if k is equal to 1, then r is 7 by 54 and
Okay.
1 by 54.
Okay, so these are the two valid solutions that we get. So basically, x is 1 plus 7 by 54, or x is 3 plus 1 by. Okay, so all of this was for the case 1 where 2r is less than 1. Okay, then similarly, we consider the case 2r greater than 1. So case 2r greater than or equal to. So in this case, now the greatest integer of 2x is no longer 2k, it has 2k plus 1. So the LHS becomes 1 over k plus 1 over 2k plus 1 is equal to 9 times r plus 1. And here, as we observed at the beginning, that just compare the magnitude of the LHS and RHS, because we now know that r is at least half. So the RHS is not small, it is going to be at least 4 by 2 plus something, going to be 9 by 2 plus something. So that is going to be 4 point something. And LHS is the sum of two reciprocals of integers. So LHS will be greater than 2 and RHS is greater than 4, which is the contradiction. So in this case too, you will not get any solution. Okay. So again, any such problem is a combination of multiple ideas. So the first idea was to make the proper cases. So cases based on the boundary where the 2x crosses the integer, right? We understand intuitively why we are looking at these two cases and not any other cases. It's very helpful to draw a few graphs. So try to plot the graph of greatest integer of x, 2x, and like what happens if you translate it by some x plus any x plus 0.4, 2x plus 0.4, etc. So this kind of basic graph if you draw it, you start to get an intuition that where the integer crossings are happening and how you should make the cases accordingly. And the second important idea is estimation. I mean, this keeps coming up again and again. Okay, so estimation is for problem solving in number theory. Estimation and bounds is very important to eliminate the number of trial and error. Right? See, in this one step, we immediately got that k is less than 9 by 2, and we just have to try 4 values of k. So that is.
In case 1, I got 2 more solutions.
Okay, tell me.
So those are 2 plus 5 by 108 and 4 plus 1 by 216, and I substituted, it works.
Okay, so you say if I put k equal to 2 and k equal to 4, we are getting that. So if I put k equal to 2, I get r is equal to 1 over 12. Is it 5 by 100 or 6 by 100?
Sir, in which case?
Oh, no.
K equal
No, I think I'm confused. Is 100 a multiple of 27? No. Yeah. Yeah, so it is 5 by 108. Yeah, that is correct. So r is equal to 5 by 108. And the second case is k equal to 4. What did you get r as?
1 by 216.
These are valid, right? Or no? Are we missing anything?
Yes, sir. Actually, I think what I did was actually I did not use that 1 2 3 4 method. I
Okay.
actually simplified it further, and I later got that 54 times the fractional part of x plus 2 divides 9. So I just took the factors of 9 as plus 1 plus minus 1 plus minus 3 plus minus 9.
Okay.
And I'm just checking like how I made this solution.
Okay. Can you tell us your calculations? It might lead to a different solution. So,
Okay, so
then should I start? Yes, but yeah, these are also valid solutions. So yeah, looks like we have total 4 solutions. Okay, one for each value.
so sir, if we start from the starting, like here, so that 3 by 2 times fractional part of x.
Okay.
So 3 by 2 times, sorry, 3 by 2 in denominator integer part of x
Okay.
minus 1 by 3 is equal to 9 times fractional part of x.
Yes.
So fractional part of x is 1 by 6 times integer part of x minus 1 by 27.
Yes.
So 6 times fractional part of x times integer part of x is equal to
Mhm.
1 minus 6 times integer part of x minus 27. So that is just 2 by 9. No, sorry, by 27.
Oh, sorry.
Yes, sir.
Wait, just a minute. We see how this.
So that by is only for minus 6 by 6 floor of x, not for
Okay.
1. So we get that 1 is equal to
No, just wait. Let me just check this step.
okay, sir.
Yeah, okay, go ahead.
Yes, sir. So now if we just translate it to the other side, we get that 9 is equal to
Hmm.
9 is equal to floor of x times 54 times fractional part of x plus 2. So
Where
that
should I put the bracket?
floor of x is outside the bracket, other thing is inside the bracket. Yes, sir. So I got that 54 times
No,
fractional part
wait.
of.
Let me again check this step.
Oh, sir, I just missed the middle calculations. That 6 by 27 becomes 2 by 9. So if we go to the other side, then the
Yes.
9 again can be translated there.
Okay, maybe we can first write it as 2 by 9.
If we take it there,
Okay,
then
multiply, let's say multiply everything by, okay, I got it. Yeah, multiply everything by 9. Okay.
okay, so now I get that 54 times fractional part of x plus 2 divides 9.
Yes.
So I got the cases where the divisors are, oh, so here it is plus 2, so the divisors count can only be plus 3 and plus 9.
No, but wait, why should this even be an integer?
Oh, yes, sir, I missed that one.
Right,
Like the 9 may just cancel with something.
right. I mean, because I think the solutions you missed were 2 and 4. So maybe those are translating to fractional values.
Yes, sir, I missed this
Yeah.
step.
Yeah. Okay. Yeah, but I'm just trying to see if we can save this solution. Did everybody follow up to this step and why here we got into trouble? Because here, if you assume that this right hand side bracket is a integer, then we'll get the valid solutions k is equal to 1 and k is equal to 3. Right? We'll get basically the fractional part is 1 and 3. And that is why we missed the two solutions where the the integer part is 2 and 4. In that case, this bracket turns out to be 9 by 2 and 9 by 4. So we missed that. But I mean, suppose we land into some equation like this, then what can we do to save at this point? Yeah, I'm not sure actually. But anyway, give it a thought. Maybe there is some way to simplify.
We can multiply the bracket and we get that 9, and we take 2 times floor of x on LHS, and we
Okay.
get 9 minus 2 times floor of x is equal to 54 times floor of x into fractional part of x.
Yes.
And now x has to be between 1 and 4. So we try 1 to 4 all the numbers, and we get respective values of fraction part of x.
Right. So at this point, yeah, kind of similar to what we did earlier. Here, the RHS, we can say that it has to be positive, or at least not greater than or equal to 0. So again, implies the same condition that we had earlier, that x is supposed to be less than 9, right? And then that puts the restriction on the number of values.
Yes, sir. Actually, I was solving never considered those bounds, so I got into trouble.
Right. Yeah. Okay. Okay, so this was question 10. But yeah, I mean, before we go to next question, just want to again highlight the fact that these are very useful exercises to do. In fact, today we didn't get a chance to do puzzle, but this is the puzzle for you. And two functions are very interesting. Okay, greatest integer of x and modulo x. Okay, these are very curious functions because of their graph. And if you have ever drawn the graphs of these two, you know modulo x looks like this. And the greatest integer function has a much even weirder graph because it is discontinuous at all the integer points. So these two graphs can be combined together to create some very interesting patterns. Like, I mean, I can ask this as a problem for you. Try to construct a function whose graph looks like this. Okay? So maybe I can give you some deliberate. Let's say I want a function which looks like this. But here it is a slope of 45 degrees up to this point. Then the function is straight line up to here. Then at let's say at 1 it goes to -2. So 1 comma -2. Then it comes back to 2 comma 0. And after a straight line, maybe to 4 comma 0. Now it again has a 45 degrees slope. Okay, so this red line, this looks like very strange. But with some clever tricks and jewelry like shift of origin and multiplication, you can construct any such function using modulus and greatest integer. In here, you don't need greatest integer also, but I mean, try to come up with a function whose graph looks like this. There is no reason for you to do this, but just a fun challenge for you to try. But the point is that you should spend enough time to try various experiments with these two functions in particular because their graphs are very weird. And they can lead to very interesting either patterns or help you to doing problem solving. Like even if you remember the problem we did last time, where we are counting the number of solutions to that other problem, right? Question 8. A very similar idea was involved there also. That if you look at the graph, you get a good intuition about what can happen. Okay, but anyway, I think we are almost out of time. So yeah, I mean, I don't have a puzzle, but yeah, you can call this a puzzle. This is kind of a well-known and it stays within the theme of number theory to some extent. So this is a game being played by two people, okay? A and B, typically Alice and Bob. And the game is like this. B has a polynomial in his mind, okay? So B has some polynomial P of x, A and x is to 1 plus A minus 1, A minus 1. Okay, and what is known to both Alice and Bob is that the coefficients are all positive or non-negative integers. So all the AIs are integers and greater than or equal to 0. Okay. So this is known to Alice and Bob. Now the goal of Alice is to guess what is that polynomial. Okay, and what Alice can do is he can ask the question. A can provide any value of x to B, and B has to reply with the evaluation of the polynomial at that time. So x B will reply with P of x. Okay, and let's say every time Alice does this, it costs her 1 rupee. Let's say okay, so 1 rupee per question or per value of x supplied. So the question is how many rupees will Alice have to spend before she can guess the polynomial correctly? And they don't know anything about the degree also. The n is also unknown. It can be linear, quadratic, cubic, x raised to 100. We don't know. So for example, if let's say Alice wants to know the constant term like A0, what is the question Alice will ask?
0.
0, right? If A asks 0, B has to reply with P of 0, which is A0. So that is how you can obtain the constant coefficient. But Alice wants to obtain the entire polynomial. So has anybody already seen this problem elsewhere? It's kind of well known. So don't know if somebody already knows the solution.
I think that if you ask n+1 questions, then this is actually solved because you will get n+1 variables and n+1 equations.
But for that you need to know what is n, right? That you don't know.
Oh, yes.
That is part of the difficulty. But yes, you are right. If you knew n, then this is like that Lagrange 0, 1 block, right? If you just evaluate the polynomial at some n+1 points, and you have enough information to construct the polynomial. And for that, you don't even require this condition of the coefficient being non-negative integers. You can do it for any polynomial.
Sir, can you just show the graph for a moment?
The above graph.
Yes, sir.
So the key points are -2, 0, 0, 0, 1, -2, 2, 0, and 4, 0. So such a function is called a piecewise linear function. So it is not a linear in the sense it's not a straight line, but piece by piece, every part of the function is a straight line.
In that, can't we just say that f of x is this if x belongs to this range, is this if x belongs to this range, and like that?
Yeah, that is of course doable. Can you come with a single formula which you just substitute a value of x and you'll get an answer? Like how mod x is, right? Mod x is doesn't have to say if x is. So you have to use mod x somehow.
Okay, sir.
Yeah, of course, that trick is always there. You write fx equal to this if this. Okay, but anyway, we are almost out of time. So we have two problems to think about. Propose what is the formula for this function and what should be Alice's strategy and how many rupees she will have to spend. I mean, your intuition with it, if n is very large, let's say n is 1,000 crore, Alice will go bankrupt very quickly. Or is it not the case? So that is the question. Okay, I think that's all for today. Thank you. Bye. But so I'll upload that problem sheet on the Google Drive and share the link so you can track questions 9 to 12 or 11, 12 also as homework.
Sir, actually, in the while you are proving that L and R, like the reduced residue one, where just a second.
No, sorry, I couldn't hear you. Can you repeat that?
Sir, while we were proving that L and R are identical model in some order of that reduced residue set, I actually came up with a different proof, which I think it's quite shorter because it does not require any mathematical calculations.
Okay, are you referring to the very first case where we are considering all residues or
No,
the
sir, no,
second
sir.
one?
Reduced residue.
Okay, okay.
So, sir, R was the reduced residue set mod n, which we know.
Yes.
So we know that no two elements of L are congruent mod n, and all of the elements of L are coprime to n.
Yes.
And also the cardinality of L is the phi of n.
Yes.
So we can just say that L is also the reduced residue set mod n.
Yeah, I think that is true.
And so L is equal to R, like with mod n.
Yeah, I think so because in the first part we already shown that the first LHS is incongruent to modulo n. So they are all distinct is already known and they are all co-prime is also known. So it has to be the same set.
Yes, sir.
Yeah, I think that's a fair point. Yeah, we can quickly jump to that conclusion.
Okay, thank you, sir.
Okay, that's all. Thank you. Bye.
Thank you, sir. Bye, sir.
Bye, sir.
Bye, sir. Thank you, sir.